Hello everyone, my name is Madiha and my topic of term project is Android operating system. In my presentation, I will talk on Android operating system and its applications architecture, Android security mechanisms, Android security issues, Android malware threats, and proposed solutions. Let's start with the introduction. Android was founded in Palo Alto, California, United States in October 2003. It was acquired by Google in August 2005, making Android a wholly owned subsidiary of Google. Each new version of Android operating system is developed under a specific code name, like Android 1.5 as Cupcake, Android 1.6 as Donut, Android 4.4 as KitKat, and Android 8.0 as Oreo. Android has gained popularity among a number of users over the past few years since its first introduction in 2008. As an open source platform that makes users to build their own applications, customize them, and use them easily without any cost. Android operating system is set over the Linux kernel. Source code for Android is released by Google under open source license. Android operating system is a stack of software components which is divided into 5 sections and 4 main layers, as shown in the figure. Application layer is the first layer. It is at the top of Android software stack. It includes both pre-installed apps and third-party apps. Next is application framework that have a set of services that runs and manages Android applications. Services are provided in the form of Java classes for applications. Application framework includes services like Activity Manager, Content Providers, Resource Manager, Notification Manager, and View System. Third is Android Runtime, in which we have core libraries and Dalvik Virtual Machine. Dalvik Virtual Machine is a Java virtual machine specially designed and optimized for Android. Dalvik VM benefits from the core features of Linux such as multi-threading, multitasking, execution, and memory management. As Dalvik uses JVM, so it provides users with a set of libraries and APIs that mainly use Java programming language to develop Android apps. The native libraries of Android have been developed on the top of Linux kernel. This layer allows the device to handle various data types and have multiple useful libraries for well-functioning of Android operating system. The bottom layer is Linux kernel, which is the basic layer of the whole system, providing basic system functionality such as process management, memory management, and device management. The whole Android operating system is developed on the top of Linux kernel with some additional architectural changes made by the Google. Next is Android application structure. Application structure consists of Android.apk package and app components. Android applications have multiple files and folders that are packed as a package with .apk extension. All app files are packaged and then signed as a single APK file. Key file in the application structure is Android manifest.xml file, which is used to describe the name, version, access rights, and referenced library files for the application. There are 4 different types of app components, and each component serves a distinct purpose. First is activities. Activity in an Android application is an individual user interface screen. Android activity is where visual elements known as widgets are placed and users can perform different actions by interacting with them. Second is services. Service is the Android way to keep a background operation going. Services are used to perform background tasks of your application such as playing music, downloading data, or uploading photos. Third is content provider. It is a component that manages a dataset, and it is also known as data store. It provides flexible and consistent way to make data available within and across different applications. Last component is broadcast receiver. It is one of the components of Android applications which is used to listen to the events generated by the Android system or other Android applications. Android have its own security framework because a strong security architecture and security programs are required to secure and open platform. Android platform offers an application environment that ensures the security of user data, applications, the devices, and the network. Multiple security mechanisms are integrated into the Android framework. They can be grouped into three general groups: Android-specific mechanisms, Linux mechanisms, and environmental mechanisms. So first group is Android-specific mechanisms, in which we have Android permission framework, application sandboxing, inter-component communication, Dalvik virtual machine, and application signing. By default, no permission is associated with basic Android application to get access to the resource. Android operating system displays all the required permissions by the application before installing an application. These permissions are to enforce restrictions on the resources of the device. User can accept or refuse them. Application is installed if user accepts. In application sandboxing, applications run in sandbox, which is also called application containerization. It is an isolated area of the system that does not have access to the rest of the system resources unless the user explicitly grants access permissions when installing the application. Android kernel implements Linux discretionary access control to protect application data or device resources from unauthorized access. Unique ID (UID) is assigned to each app process within an isolated sandbox. Next is inter-component communication. Android enables applications to communicate with each other through a well-defined mechanism called inter-component communication, or binder. Application can call other application components as a service. In Dalvik virtual machine, each application runs in its own virtual machine. This prevents buffer overflows, remote code execution, and stack smashing. Next security mechanism is application signing, in which applications are digitally signed in order to install and run on Android operating system. Author of application is identified by Android operating system by application signing mechanism. Second security group is Linux mechanisms, in which we have POSIX users, file access. A unique Linux user ID is assigned to each Android package file that is installed on a device. This way, two different package code can't run in the same process, prevents applications from interfering with one another. Android files are under the Linux permission mechanism. Each file has owner's user ID, a group ID, and three tuples of read, write, and execute permissions. So assigning different users with proper permissions for each application and system files provide needed security for file access and prevents one application from accessing another app files. Last security group is environmental features, in which we have a memory management unit and type safety. Linux have a memory management unit that facilitates separating processes into different address space. This helps in ensuring that one process cannot read another's memory page or corrupt them. We know that partial or missing boundary checks can lead to memory corruption and buffer overflow attacks. So Android type safety property forces variable contents to follow a specific format both in compiling time and runtime to prevent buffer overflows, stack smashing, or undesirable usage. Android have security issues that can lead to user information leakage or can put user privacy in danger. First issue is privacy or information leakage. The permission control mechanism for Android is proven to be ineffective in protecting user privacy and resource from malicious applications. Because only a small percentage of users notice to the resources being requested when installing a new app. Inexperienced users are not aware of irrelevant resource requests and will compromise their privacy by unknowingly allowing access to the sensitive data. Privilege escalation or permission escalation attacks are the attacks that exploits Android kernel vulnerabilities to get access of the resources that are usually protected from an application or user. Sensitive information can be leaked by such attacks as they result in unauthorized actions from applications with more privileges than intended. Next is repackaging apps. It is one of the most common security issues of Android operating system. Repackaging is a technique of deassembling or decompiling .apk files using reverse engineering and injecting malicious code into main source code. Repackaging technique is used on the Android platform to allow malicious code to act as a normal app. So differentiating between a repackaged malicious code and a normal app is difficult because repackaged apps usually work in the same way as the legitimate apps. Next we have denial of service attack. Most smartphones do not have the same protection as our personal computers. Like smartphones do not have antivirus programs. So malicious applications find smartphones a suitable platform for DOS attacks. This attack may occur when apps overuse limited CPU, memory, bandwidth resources, and restrict the execution of normal functions by users. Android have the following main malware threats: Trojan, adware, rootkits, ransomware. Trojans basically act as benign apps, but they do harmful activities without users' consent and knowledge. Unauthorized access to the victim's device is given to the attacker by Trojans, and additional malware is downloaded on the device to leak the confidential information or to steal sensitive data of users like passwords. Adware, it is the most common app-based mobile threat. Aggressive type of adware is hidden inside Android apps, usually found in third-party apps. They create shortcuts on the home screen, steal bookmarks, change default browser settings, and push unnecessary notifications to prevent effective use of device. Plankton is a popular aggressive adware. Rootkits, it's a type of malware in which attacker get control of the targeted device, spy on the user browsing habits, emails, and steal credentials. Ransomware is a type of malware that encrypts user data or lock user device, making the device or data inaccessible until ransom payment is done. For example, Fake Defender acts as a Avast anti-malware. It locks the device and demands for ransom to unlock the device. Considering Android security issues and threats, we have tools and techniques that use a static and dynamic analysis approach. In static analysis, the main techniques are application signature, permission analysis, and component-based analysis. Android applications have a unique signature. Signature-based solutions check application contents or patterns against malware signature dictionary. They take action if they find a match. And this approach is somewhat limited because only limited number of emerging threats can be identified. Permission analysis approach works on the basis of permissions that are granted to the application. Risk of granted permissions and the sensitivity of the resources is assessed, and malicious apps are detected and analyzed based on that assessed risk level. In component-based analysis, an app is deassembled to get important content such as Android manifest.xml file, resources, and bytecode to do detailed app security assessment and analysis. Components definition and bytecode interaction is analyzed using app security and assessment solutions to identify the vulnerabilities. Kiran and Droidmos are the mechanisms that use static methodology. Droidmos is proposed for app similarity measurement and to effectively locate and detect the changes from app repackaging behavior. It uses fuzzy hashing technique. It is basically suggested to identify repackaged applications on third-party Android marketplaces by measuring similarity of third-party app with apps from the official Android markets. Kiran Main objective is to mitigate malicious apps at installation using certification process on apps. The rules are determined on the basis of permissions that are sensitive and can lead to misuse of permissions and fatal activities. A set of predefined security rules are used by Kiran on the requested permissions of app to find matched malicious permission requests and characteristics. Installation is prevented if an application fails to comply with the security rules of the Kiran. Static analysis techniques are efficient and quick, but they failed against encrypted, polymorphic, and code-transformed malware. Dynamic analysis learns application interaction by executing app in protected environment with sufficient emulated resources it needs to identify malicious activities. Bouncer and AppGuard are the two mechanisms that use dynamic analysis methodology. Google own App Store Google Play is protected by the Bouncer system. Third-party developer apps are first tested by the Bouncer, which is a virtual machine based on dynamic analysis platform, before they are used by the users for download. Apps are executed by it to look for any malicious behavior and compares it to previously analyzed malicious apps. AppGuard is a flexible system for enforcing user-customized security policies on untrusted Android applications. It works on the basis of inline reference monitoring, and predefined user policies are enforced on third-party apps. A security call is executed before each function call into the Android system libraries. Security Monitor checks whether the security policies currently enforced allow the system call from the application, and then looks for users' predefined policy to execute or deny the requested permission. Android is a very huge domain, and it is a code delivery platform for smartphones, providing services globally. There is a daily increase in the number of Android apps, including malwares, due to the increasing popularity of Android smartphones. Android security architecture have been adopted to improve the security of the system and to protect data. But despite of the Android security mechanisms, malware is taking advantage of security holes in Android to misuse the resources. Many techniques have been proposed to limit vulnerability outreach in Android devices, but many issues and challenges still exist that should be resolved to become fully pervasive. Thank you for listening, and please let me know your comments or questions if you have any. Thank you so much.